the force that shouldn't exist. What if I told you the very reason you're here, the reason galaxies formed, stars ignited, and life exists, comes down to something we can't even see? A force that pushes the entire universe apart. A force that defies gravity. A force so strange that our best physics predicts it should have destroyed everything before anything began. They call it dark energy. But make no mistake, there's nothing dark about its impact. It dominates our cosmos, controls the fate of everything, and could one day tear the universe to pieces. Still, we barely understand it. We don't know where it comes from. We don't know why it's so perfectly balanced. And we have no idea how this ends. Tonight, we're going to uncover what scientists have learned about this invisible power. We'll journey from the tiniest quantum fluctuations to the outer edges of space and time, where stars vanish, galaxies disappear, and the laws of physics might no longer apply. So lean in and ask yourself, if the universe has an end, what does that mean for everything we know? And more importantly, what does it mean for us? What is dark energy? Before we can understand how the universe might end, we have to understand what's pushing it apart in the first place. This invisible something, this silent, all-powerful force that seems to be stretching the fabric of reality itself. It isn't matter. It isn't light. It doesn't behave like anything we've ever touched or seen. We call it dark energy. But let's be clear. Dark doesn't mean evil. It simply means unknown, unseen. And yet, it's everywhere. According to the best measurements we have, about 68% of the entire universe is made of dark energy. Not stars, not gas, not even the mysterious dark matter that holds galaxies together. No, dark energy is bigger than all of that. It's the force that dominates the cosmos. A short trip back in time. Let's rewind to the 1920s. Astronomer Edwin Hubble discovered something extraordinary. Every galaxy in the universe is moving away from us. The farther it is, the faster it goes. It was the first real evidence that the universe is expanding. And for decades, scientists assumed that expansion would slow down, thanks to gravity. After all, gravity pulls things together. So, surely, over time, the universe would decelerate, maybe even collapse back in. But then came the shocking twist. In the late 1990s, astronomers measuring distant supernova found something they didn't expect. The universe isn't slowing down. It's speeding up. That changed everything. The acceleration nobody saw coming. To explain this unexpected acceleration, physicists needed a new kind of energy, something that doesn't pull, but pushes. A form of energy woven into the fabric of space itself. That's dark energy, the force that makes more space. And the more space it makes, the more energy there is to keep making space. It's a feedback loop that could, quite literally, go on forever. Einstein once proposed something like this: a cosmological constant, and then called it the biggest mistake of his career. Turns out, it might have been his greatest insight. But what is it, really? That's where things get weird. There are two leading theories right now. Theory 1. Dark energy is the energy of the vacuum, an unchanging background force, constant across time and space. Theory 2. Dark energy is tied to a new kind of field, made of unknown particles that evolve over time. Something dynamic, shifting, unpredictable. And each theory points to a completely different fate for the universe. One leads to eternal stillness, another to sudden collapse, or chaos, or rebirth. To make matters worse, we've tried to calculate how much dark energy there should be. And the answer we get? It's off by a factor of 10 to the 120th power. That's a number so wrong. It's been called the worst theoretical prediction in the history of physics. Something's not adding up. A mystery at the heart of reality. Dark energy breaks our rules. It defies our equations. It shouldn't exist in this form. And yet, without it, the universe as we know it wouldn't exist at all. It's not just a scientific puzzle. It's a paradox. The deeper we go, the more it feels like dark energy is the key to everything. The fate of the universe. The nature of time. Even the question of why we're here at all. And now that we understand just how bizarre and powerful this force is, let's explore what it might do next. Because if dark energy is real, and all evidence suggests it is, then it holds the pen to write the final chapter of the cosmos. The fate of the universe. 4 possible scenarios. Now that we know dark energy exists, this force that shouldn't be, we face an even bigger question. What happens next? The future of the cosmos hinges on the true nature of dark energy. And while we don't have all the answers yet, physicists have drawn up 4 distinct endings to our story. 4 ways the universe could die. Or be reborn. Let's explore them, one by one. The Big Freeze. A cold and lonely ending. Imagine this. Billions of years from now, the last stars have burned out. No light, no warmth, just endless, expanding darkness. This is the Big Freeze, also known as heat death. But don't let the name fool you. There's no heat. If dark energy remains constant and unchanging, like the energy of a stable vacuum, then space will continue to expand forever. Galaxies will drift apart. Even light won't be able to cross the ever-growing gulf between them. Eventually, black holes will evaporate. Atoms will decay. And the universe will become a silent, featureless void. No temperature gradients, no usable energy. Just stillness. It sounds tragic. But for some scientists, it's the most peaceful ending possible. The Big Rip, when the universe tears itself apart. But what if dark energy isn't constant? What if it grows stronger over time? Some theories suggest dark energy could belong to an exotic class of fields called phantom energy, a force that gains energy as it expands. And if that's true, the consequences are terrifying. First, distant galaxies will accelerate away. Then gravity itself will lose its grip. Solar systems will fly apart. Planets will disintegrate. Even atoms will be ripped from their nuclei. In the final moments, the universe won't just die. It will be shredded. Time ends in a screaming crescendo of heat, light, and raw energy. They call it the Big Rip, the Big Crunch, the return to the beginning. Now let's flip the script. What if dark energy fades over time? What if it stops pushing altogether? In this case, gravity gets the final word. The universe slows down, then stops, then begins to collapse inward. Galaxies rush back together. Stars collide. Everything converges into a single fiery point, hotter than anything imaginable. This is the Big Crunch, the mirror image of the Big Bang. But here's the twist. Some physicists think that after the crunch, the universe might bounce back. A big bounce, a new Big Bang, a new cycle. Maybe this isn't the first universe. Maybe it won't be the last. What if time is a circle? Vacuum decay, the quantum catastrophe. And then there's the weirdest fate of all. Remember how the vacuum of space might not be truly stable? This quantum leap would rewrite physics. Particles would change. Atoms would cease to exist. The very fabric of reality would collapse into a new version of itself. One where life as we know it is impossible. No warning, no escape. Just blink. Gone. They call it vacuum decay. It's the kind of end that would rewrite the laws of everything, if there's even anyone left to notice. 4 fates, each more mysterious than the last. A frozen void, a violent tear, a fiery collapse, or a quantum reset. The truth is, we don't know which one is coming, but we're starting to learn which ones are still on the table. And the secret to finding out? It lies in solving one of the greatest mysteries in modern physics. So what's the problem? If lambda represents the energy of empty space, the vacuum, then physics should be able to calculate how much energy that vacuum contains. And we tried. Using the best tools we have, quantum field theory, scientists calculated the amount of energy that should exist in every cubic meter of empty space. The result? A number so large, so absurd, so off the charts wrong. It defies belief. It was 10 to the 120th power times bigger than what we actually observe. That's a 1 followed by 120 zeros. If you're wondering how bad that is, it's been called the worst theoretical prediction in the history of physics. It's not just wrong, it's embarrassingly wrong. A cosmic coincidence? Here's what makes it even stranger. If dark energy had been just a little bit stronger, galaxies would never have formed. Stars would never have ignited. Atoms may not have bonded. And if it were just a little weaker, gravity would have crushed everything back down in a fiery collapse. Somehow, against all odds, the number was just right. Not too big, not too small, just perfectly balanced for life to exist. It's like throwing a dart at a dartboard the size of the universe and hitting a bullseye the size of an atom. That's how precise the cosmological constant had to be for you to be watching this video right now. How do we make sense of that? There are a few possibilities. Pure chance. We just got lucky. The universe rolled the dice, and here we are. Fine-tuning. Maybe the universe was designed this way, by a higher intelligence or hidden order we can't yet detect. Or there's something else entirely. What if there are other universes? Countless ones. Each with different values of dark energy. Most too high or too low for life. But in the tiny sliver where it's just right, intelligent life can arise. And ask these exact questions. This is the beginning of the multiverse hypothesis. A bold, mind-bending idea that could explain why we exist at all. And it might be the only way to solve this cosmic math problem that refuses to go away. The cosmological constant doesn't just challenge our equations, it challenges our sense of reality. Because if something this wrong can still give birth to a universe this right, then maybe our universe isn't the only one. Let's explore that next. Why are we even here? Pause for a second. Take a breath. Look around. At the planet beneath your feet, the stars overhead, the thoughts in your mind. And ask yourself the most unsettling question in all of science. Why are we even here? By all logic, we shouldn't be. According to the best physics we have, our universe shouldn't exist. At least, not like this. Not with galaxies, not with stars, not with life. The amount of dark energy in the universe, the cosmological constant, isn't just mysterious. It's shockingly perfect for life to exist. Too much dark energy, and the universe would have expanded too fast. Matter would have spread out before it could ever clump into stars or planets. Too little dark energy, and the universe would have collapsed back in on itself before anything had a chance to form. But somehow, the value we observe isn't off by just a little. It's off by an unimaginable amount. The most impossible coincidence in physics. To put it simply, physicists expected the vacuum energy of space to be huge. Statistically speaking, the odds of getting a number this precise by chance are so low, you'd be more likely to win the lottery every day for the next billion years. It's like flipping a coin 100 times and getting heads every single time. So what gives? Why does the universe seem so perfectly calibrated to allow us to exist? One explanation is known as the anthropic principle. And it goes like this. Maybe the universe isn't fine-tuned for life. Maybe we just happen to be in one of the rare universes where life is possible. Think about it. If there were a trillion universes, each with slightly different laws of physics, then most of them would be dead, sterile, and empty. But in the tiny fraction where the conditions are just right, life would arise and ask, why is the universe so perfect? The answer? Because only in a universe like this could that question even be asked. Multiverse, the landscape of possibility. This leads us to one of the boldest ideas in modern physics. Maybe our universe is just one bubble in a vast multiverse, a cosmic landscape filled with countless other universes, each with different values for dark energy, gravity, particle masses, even time itself. Most of these universes are stillborn, lifeless, silent. But a few, maybe just a handful, have the right ingredients for galaxies, stars, chemistry, and eventually, consciousness. And in one of those, you're here, watching this video, wondering how you got so lucky. If we really are living in a multiverse, just one lucky universe among countless failures, then maybe the biggest question isn't why us. Maybe it's, are there others? And that is exactly where we're headed next. The multiverse hypothesis. If the universe is so precisely tuned for life, then maybe it's not the only one. What if our cosmos is just one page in an infinite library? Welcome to the multiverse. What is the multiverse, really? The word multiverse sounds like science fiction. But in physics, it's become a serious proposal to explain one of science's most baffling puzzles. Why is our universe so perfect for life? And here's the key idea. If countless universes exist, each with different physical constants, then it's no surprise that one of them looks like this. It's not magic. It's not destiny. It's statistics. But not all multiverses are the same. In fact, There are at least 3 major types that scientists are exploring, each more mind-bending than the last. Let's dive into them. The temporal multiverse, universes through time. This is the idea of cyclical universes, one after another, through time. In this model, the universe goes through an endless loop. Big bang, expansion, contraction, big crunch, big bounce, repeat. Each cycle could reset the physical laws slightly, like rolling cosmic dice. And every new universe born in the bounce might have different versions of dark energy, gravity, or matter. We might be in cycle number 1, or 1 trillion. Maybe the Big Bang wasn't the beginning. Maybe it was just the latest reboot. The spatial multiverse, universes beyond our horizon. Imagine zooming out, way out, beyond what any telescope can see. In inflation theory, space didn't just expand after the Big Bang, it inflated, explosively, in all directions. And in some versions of this model, inflation never fully stopped. It kept going in distant patches of space, creating entire new regions, each cut off from the others. These patches became their own universes, with their own physics and their own destinies. They're so far away that light will never reach us from them. We can't see them, can't touch them. But according to some cosmologists, they're out there, right now. The quantum multiverse, every possibility. Real. This one's the strangest of all. And it comes from quantum mechanics. At the smallest scales, particles behave unpredictably. They exist in superpositions, in multiple states at once. And every time a measurement is made, the universe chooses one outcome. But in the many worlds interpretation, it doesn't choose. All outcomes happen, each in a different branch of reality. No telescope has glimpsed them. No probe has measured them. But they solve problems that nothing else can. They explain why our universe has just the right conditions for life, without needing miracles or design. In that sense, they're not just science fiction. They're scientific necessity. Maybe one day, we'll find a way to test them. Maybe future generations will look at our universe and recognize it as just one entry in a vast cosmic archive. Or maybe not. But whether they're real or not, the multiverse idea changes how we see ourselves. Not as the center of creation. In a multiverse, we are not special because we were chosen. We're special because we made it. Out of infinite chances, could dark energy be hiding in black holes? We've always thought of black holes as the end of stars, the end of information, the end of understanding. But what if they're also the beginning of something else? What if, inside the most mysterious objects in the universe, lies the key to dark energy itself? Black holes, not what we think. Here's what we know. When a massive star dies, it collapses under its own gravity, forming a black hole, a point of infinite density surrounded by an event horizon. Nothing escapes, not even light, not even time as we know it. But the truth is, we don't really know what happens inside a black hole. Our equations break. Physics goes silent, and that silence might be hiding a secret. Imagine a star with no singularity, no crushing center, just a shell containing a core of dark energy-like vacuum. From the outside, a gravastar would look exactly like a black hole. It would bend light, it would swallow objects, it would warp space-time. But it wouldn't be a hole. It would be a container. Dark energy. Observational clues, a growing mystery. In 2023, a controversial paper sent ripples through the astrophysics world. A team of researchers analyzed the growth of supermassive black holes at the centers of galaxies, and found that their mass was increasing in exactly the same pattern as the expansion of the universe. Black holes aren't just growing. They're growing with the universe. Black holes might be dark energy, or at least hiding it. Skepticism and scientific fireworks. Of course, not everyone agrees. Many astrophysicists argue that the data isn't solid, that black holes should grow due to accretion and mergers, not cosmic expansion. Others say the math behind gravastars is still too speculative. But here's the thing. If gravastars do exist, they might solve two cosmic mysteries at once. What is dark energy? What's really inside a black hole? That kind of explanatory power is hard to ignore. If it walks like a black hole, the deeper question becomes this. If something bends light like a black hole, eats matter like a black hole, acts like a black hole, but isn't one, should we still call it a black hole? Or are we staring at a completely different kind of cosmic object? Something that challenges the way we've defined the end of stars and the energy of space itself. Dark energy isn't out there in empty space. Maybe it's inside the very monsters we've been afraid to look into for so long. Because sometimes, the answers we're searching for in the farthest reaches of the cosmos are hiding in the darkest corners of our own equations. Are we lucky or designed? We've traveled far. From quantum ripples to cosmic fates. From collapsing stars to invisible forces. To the very question of why anything exists at all. And now, as we stand at the edge of what science can explain, we're left with a haunting question. Is this all just luck? Or was it designed this way? The perfect shot in the dark. Think about it. The cosmological constant, the energy of empty space, had to fall within an impossibly narrow range for life to exist. A universe worth wondering about. Maybe it's all a happy accident. Maybe it's part of something greater. Maybe we're just beginning to understand the rules of a game that's far bigger than we ever dreamed. But whatever the truth is, isn't it amazing that we get to be here to wonder about it? That out of all the chaos and silence and stars, we get to ask questions, we get to build telescopes, we get to feel awe. Maybe the universe isn't just cold equations after all. Maybe it's also a mirror, reflecting back the curiosity that lives within us. We don't need all the answers to appreciate this miracle we're living in. We just need to ask the questions. I'm truly grateful you stayed for this entire journey. If you found value in it, give it a like and maybe a sub, so we can explore even further together. Thanks for being here. See you in the next one. And remember, the sky isn't the limit. It's just the beginning.